Hi, so this is the second video in the elements, mixtures, compounds. The first one was about the elements that are on the periodic table. So in this video I want to talk about elements coming together and actually making the compounds that we've been talking about. And then I thought about when I would teach this, I would definitely use the word substance. And I thought it's perhaps best to just start off talking about that, about why this word substance is used and what it means. So substance is one of these vague words which means chemical or material, whatever it is we're talking about, when we don't know really what it is that we're talking about, or we don't want the audience to know exactly what it's talking about, so we use the word substance. So when we've got material, we don't really know what material it is, or we don't want other people to know what it is, then we might use the word substance as a suitably vague word when speaking about the material or chemical. So substances can be pure, like water. So say I give you a colourless liquid, I say that's substance, what is it? Later you might find out boils at 100, melts at 0, therefore has to be water. But what about things that are not pure? What about salty water? Well, salty water would be what we call a mixture. Salty water would be a substance, and we would perhaps give it to you. It would look the same as water, but it wouldn't be water, would it? It would be different. It would be a mixture because it would have water in it and it would have salt in it. Salt and water, the whole thing together is a mixture. So you need to know the word mixture is two or more different particles being present, whereas water would be just water particles being present. So a pure substance would be made of one type of particle, whereas a mixture would be two or more different kinds of particles in the same container. Right, I don't want you to learn those. They're not definitions. They're just understanding. When we use phrases like substance, when we use phrases like mixture, they're vague and suitably vague, and then I can go on to today's lesson, which is more about elements, mixtures and compounds. So we've already talked about what an element is. We've already come across this definition. When a substance is made up of atoms that all have the same number of protons, then that substance is an element. I ended my last video making the clear point that it's the number of protons that fundamentally define what element you have. If you know the number of protons that you've got present, you don't always. So, the first new thing today, I want you to learn. Definitions to learn. They're not vague. I want you to learn this. Normally, when they ask the question, define a compound in an exam, there are 2 marks. 1 mark for saying a compound is a substance, like that, suitably vague. A compound is something that is made up of 2 or more elements. That's 1 mark. That nets you 1 mark. 2 or more elements. 1 mark, and then chemically bonded together. That's the 2nd mark. So 1 mark there, 1 mark here, 2 marks. Then that substance is a compound. So let me read it all in one go. When a substance is made up of 2 or more elements chemically bonded together, then that is a compound. Learn that. Pause it, write it, practice it, and then we can move on. Well, we have to give you some examples, and I'm going to run through, I think, 3 examples or 4 examples. I can't remember how many I've got on my slides. I'm going to run through water first. Now, water, you're familiar with water. You come to us from general science where you know water is H2O. H2O. H stands for hydrogen. It's a symbol for hydrogen, H. O, symbol for oxygen. Hydrogen and oxygen join together. Hydrogen is an element, oxygen is an element. The two elements join together and make water, which is H2O. Now what does that 2 mean? Well, the 2 means for every 1 oxygen, you've got 2 hydrogens present. So in terms of quantity, if you had gases, for every 2 litres of hydrogen, 1 litre of oxygen would be needed to join them all together. It's a ratio. These small numbers, we always write them subscript. That means we write them down a bit. The small numbers written down a bit, the subscript numbers, tell you the ratio of the elements that are present within the compound. And with water it's H2O. Now, that says what I've just said to you. The common name for it is water, but the chemical name is hydrogen with oxygen, hydrogen oxide. Hydrogen oxide is the common name for water. Now there's 2 ways I want to talk about this as a compound. What if I give you a balloon? I give you a balloon, and in the balloon, it's a 3 litre balloon. I fill it with 2 litres of hydrogen, 1 litre of oxygen. Can you see that's the ratio 2 to 1? Those 3 litres in a balloon, the chemicals inside, the gases, would mix completely with each other, and then if I was to take a match and light that balloon would explode. That would be dramatic. And in the old days, when I first started teaching, we would do that. We would explode hydrogen and oxygen in small balloons, and then some safety aspect came in and said that no, we shouldn't be doing that. It's too loud a noise. They're probably right, because over the years my hearing has deteriorated, maybe because I was doing those loud explosions when I was younger, or maybe it was the heavy rock music I listened to when I had long hair many moons ago. Who knows? But my hearing is not good, and it may have been that. It may be that the safety advice is wise, whereas Ahmed, as a young man, was not wise. Well, what about the opposite of that? Well, the opposite of a compound, is if we start with a compound. So say we start with water. Can I break the water down? We know it's made of hydrogen and oxygen. Can I break it down into the separate elements that make that up? And the answer is yes. We can do both of those things. We can make the compound water, and we can break the compound water down into the elements. When we're breaking it, we use electricity. We pass electricity through it, and then the electricity will cause the hydrogen and the oxygen to separate from each other, and we get the gases that make it up, we get them back again. So water can be broken down by passing electricity through it, thereby making the hydrogen and oxygen gases from it back again. So I've got little pictures of these which I can talk through. When we used to explode balloons of hydrogen and oxygen, that's what it looked like. They were dramatic. You got a ball of fire, although it was over so quickly, you could never capture that. Nowadays, with modern slow-mo cameras, etc., people can capture it. But it was hard. You heard it. It was deafeningly loud. There are reports of teachers in my era when I started teaching that would light big balloons and windows would blow out with the shock wave of the explosion that used to go through the classroom. I was only ever brave enough to do small ones, a bit like the size of a grapefruit. I never really was brave enough to go bigger than that. But they were loud enough. They were loud enough. When you do that, the rubber of the balloon, if you look at it after the explosion, the rubber of the balloon is damp, and it's damp with the water that's been made. You do a 3-litre balloon, you get drops of water. You don't get much. Drops of water. Well, what's the opposite of that? Opposite of that is if you take water and pass electricity through it. Now, I found this image on the internet. I thought that was really quite an interesting image, because you need a positive and a negative. You need DC current, and these batteries, PP3 batteries, they have a positive and a negative. I don't know which way round they are now, but it'll be written on the sides here. And when you put them into water, clearly there'll be bubbles on this side and bubbles on that side. One of those will be hydrogen, the other one will be oxygen, and they'll both be bubbling off up, and you could put test tubes over the top, and you could collect the hydrogen and the oxygens separate, and you would find you would get double the volume of hydrogen as you would the oxygen. Good experiment. So either way, that would teach you something about compounds, either breaking them down like that one, or making them like lighting hydrogen and oxygen together to make a damp balloon, the dampness being the water that you've made. Okay, that's one example. What other examples? Well, hopefully you will get to do this as a practical. Now this is iron 2 sulfide. The 2 tells you what kind of iron you've got. There are 2 kinds of irons in the world, and the iron 2 is different to the iron 3, and the Roman numerals in brackets is needed with some chemical names, and when it's needed we'll put them in, and when you do A level you'll know where to put them in, but until then you just put them in. The formula FeS, 1 Fe, that's an iron, 1 iron with 1 sulfur, 1 to 1. The ratio is 1 to 1. No small numbers. Whenever there's no number, it means 1. So 1 iron to 1 sulfur. Ratio 1 to 1. What we do here is we take iron filings, which are like iron powder, grey powder, and you mix it with powdered sulfur, which is yellow powder, and the grey powder and the yellow powder, you mix it together. That's a mixture. And then you put that in a test tube, a diddy little test tube called an ignition tube. Put it in an ignition tube. You get a little ignition tube holder, which we use clothes peg, the wooden clothes peg, and you hold it slight angle but almost horizontally in a Bunsen burner flame. So in an ignition tube you heat it strongly, and the 2 elements, then they start to join together. The heat makes them join together. As they do so, this joining, they'll give off some heat energy. As they give off the heat energy, that ignition tube will glow red hot with the heat that's coming off. So you heat it with a Bunsen burner, but when it starts glowing, you don't need to heat from then on. From then on, it'll sustain itself. The heat of the reaction will keep the test tube glowing red hot until all of the iron has reacted with all of the sulfur, until one of them runs out. So you've got 2 of them, 2 elements, they start joining together. When one runs out, then the other one is left extra. And when things are extra, in chemistry we use the phrase excess. So the extra will be left excess. So as the chemical bonding happens, a lot of heat is released, and this is seen in the test tube as it glows red during the reaction. I think I've got a photo. There. This is glowing red. That's where the sulfur is joining the iron to make the iron 2 sulfide. The yellow you can see is sulfur powder. maybe the grey you can see, maybe some iron powder that you started with. But overall, we're left with a lump of iron sulfide, which is a new which is a new compound. It's a new compound that's made from those two elements, iron and sulfur, making that lump of iron sulfide. Now, perhaps I should make the following point, which I should have done with water really. Say you've got an element here and an element here, and they join together to make a compound. The properties of that new compound are nothing at all, nothing whatsoever to do with the individual elements that make them up. So if we talk about water, for instance, hydrogen, colourless gas, oxygen, colourless gas. When you join them together, water is nothing like hydrogen and it's nothing like oxygen. It's got its own properties completely, which may be totally separate and different to the hydrogen and the oxygen that make it up. Do not extend the idea that whatever elements are used to begin with, that their behaviour, their properties will be shown in the compound that finally results as a consequence of the two elements joining together. And in this one, iron 2 sulfide is nothing like iron, it's nothing like sulfur. If you want to know its properties, you've got to do your own experiments on this. Treat it exactly like a brand new novel chemical you've not come across before, and that is a healthier way to think about compounds. Do not extrapolate the properties of the individual elements onto the compounds that they make. So, what else? Well, again, this one I hope you will do practically. So you take zinc chloride as a compound. How do you know it's a compound? Well, the name gives it away. Zinc with chlorine as a compound. So zinc chloride compound will be zinc and chlorine joined together. If you take that chemical, zinc chloride, and dissolve it, then you get a solution of zinc chloride. Now, a bit like we did with water, what if you pass DC electricity through it? Well, that DC electricity will break down the zinc chloride. It'll break it down into zinc and chlorine. Now, zinc and chlorine, they are the two elements that make it up. And again, zinc chloride properties will be entirely different to the zinc and the chlorine individual elements that make it up. And you get the zinc will be formed at the cathode, which in chemistry is a term for the negative side of the battery, the electrode, and you get bubbles of chlorine, which is a green gas, and the positive, which is the, in chemistry called the anode side of the circuit. So you get typically one element at one electrode, the other element at the other electrode. The DC electricity is very good at breaking down compounds that have been made, and we use it there to break down zinc chloride into its individual chemicals. Now, word of warning I've written at the bottom here: chlorine is poisonous. I know you say you go to swimming pools and that smell is chlorine, and you're right. The level of chlorine in a swimming pool is checked and double checked. Check it's not too high. In a school, it can get too high if you're stupid with it, so don't be stupid with it. Two things to do: one, do it in a fume cupboard, and two, you don't want to be making much of it. Make a little bit, make a few bubbles, see the bubbles. Maybe a little bit will escape out of the fume cupboard and you'll smell it like a swimming pool smell. But you should not be smelling big quantities of chlorine. It should not be like gagging you or choking you, because then that's too much. And in that way, when you do it inside a fume cupboard, make a little bit, it's entirely safe. I don't want you to be scared of chemistry. I want you to do the chemistry you're meant to do, but do it safely. I think I'm coming to the end of my compounds discussion. I've got a little diagram here which I've taken off the internet. It's not very well readable, I'm afraid, but they've got 2 carbon rods as electrodes going into zinc chloride, and the zinc chloride is being pulled apart. Zinc is going to one of these electrodes, the cathode, and chlorine ions are going to the other one, making chlorine gas. So you get zinc on one side, chlorine on the other side. As I say, I would want you to do this, and I'd want you to learn that you can break down compounds into the elements that make them up, which are simpler. So that non-definition I don't want you to learn. That elements cannot be broken down into anything simpler. Well, compounds can be broken down into things simpler. And you could argue that the zinc and the chlorine are more simple or simpler than the zinc chloride that we started with. Right? I'll stop there. I'll see you next time when I think I'm going to launch into atoms. That's for next time.